Hi, my name is Jacob Zettelman from Fermilab, and I'm going to speak about PIP2-BD, an effort to search for new physics using a stopped-pion neutrino source at the Fermilab accelerator complex in the PIP2 era. Only 1.1% of the protons produced by PIP2 are needed to support the DUNE program. What could we do with the rest of the protons? Well, low-mass dark matter searches are enabled at PIP2 with the addition of an accumulator ring and a beam dump, and we studied three possible accumulator ring scenarios. The PIP2 accumulator ring, or PAR, and the compact accumulator ring, or CPAR, can be built within the decade. The idea of CPAR is to enable beam pulselets of about 20 nanoseconds while enabling 100 kilowatts of beam power, which is key to greatly reducing backgrounds for new physics searches. The rapid cycling synchrotron storage ring, or RCS-SR, is on a long-term time scale, but would enable a megawatt-class stopped-pion neutrino source. We are considering a 100-ton scale liquid argon scintillation-only detector as the baseline detector for the PIP2-BD program. We created a custom J-force simulation to study the light collection properties and to simulate possible backgrounds. A diagram of the simulated detector is shown on the bottom left side of the poster. There are many possibilities for dark sector searches with a stopped-pion neutrino source and a large-scale detector in place. The PIP2-BD detector is sensitive to a wide range of low-mass dark sector models, and we show sensitivity studies to some specific models. The first is a vector portal model where the neutral pions and etas produced in the proton collisions produce mediators between the standard model and the dark sector. The dark matter detection mechanism in PIP2-BD is a low-energy nuclear recoil in the liquid argon. The topmost plot on the right side of the poster shows the sensitivity of a 5-year run with the baseline PIP2-BD detector to the minimal vector portal kinetic mixing model, including background estimates. The plot below that shows the sensitivity to the leptophobic vector portal model where the dark matter couples to quarks, also including background estimates. For both of these models, the PIP2-BD detector rules out large regions of parameter space and reaches below the thermal relic density line, with CPAR providing the best reach. An inelastic dark matter or IDM model extends the vector portal scenario to include two dark matter particles where the detection mechanism is either decay to E plus E minus or up or down scattering of dark matter off electrons. The third plot going downwards on the right side of the poster shows the 3-event sensitivity in the parameter space for the IDM model for a 5-year run of the PIP2-BD detector under the RCS-SR scenario without estimating backgrounds. Lastly, axion-like particles, or ALPs, that couple to photons can be produced in the beam dump via the Primakov process and detectable via the inverse Primakov process or decay to 2 photons. Also, ALPs coupling to electrons are detectable via inverse Compton scattering, E plus or E minus conversion, or decay to E plus or E minus. The plots on the bottom right of the poster show the event sensitivity for a 5-year run in the PAR and RCS-SR scenarios with a detector threshold of 100 keV. The left-hand plot shows sensitivity to ALPS coupling to photons, where PIP2-BD can cover the cosmological triangle region. The right-hand plot shows sensitivity to ALPS coupling to electrons, where PIP2-BD can test new parameter space for the QCD axion. If you're interested in learning more about the PIP2-BD facility and program, please read our white paper. The link is on the poster or come visit during the poster sessions, and thank you for listening.